This paper is about machine-independent characterization for a certain class of transducers. I will begin by explaining the terms used in the title. First, transforming. Here by transforming, I mean string-to-string transformations. Here is an example. In the input string, whenever there is a repeated occurrence of a letter, in the output I want it in quotes. Here, for example, this is a repeated occurrence of S, so it is put in quotes, and so on. You can imagine that these kind of transformations can be done by finite state machines. They are called transducers. They are machine models that implement such transformations. The next term in the title is Datawords. They are strings over infinite alphabets. Here is an example of a kind of a log of requests by processes. This is a request for a printer by process P23, another request for disk write by processor P84, process P84, and so on. So this P23, P84, and so on can be considered as process IDs, and they come from an infinite set of process IDs. Now I want a transformation which extracts all the printer requests. The first printer request is by P23, the next one is by P398, and so on. Now, to specify a device which does this, you cannot say that, well, if you see P23, then do something. If you see P398, then do something. You cannot say like that, because if you start saying like that, then you'll have to say such things for infinitely many letters. We want a device which is finitely describable. So these letters which come from an infinite set are called data values, and strings over such data values are called data words in the literature. Actually, in the literature, what is called a data word is every position contains a letter from the finite alphabet and a letter from the infinite alphabet. Here, just for simplicity, I have not used that in this example, but in general, when studying the language theory, we assume that every position contains a letter from a finite alphabet and a data value from the infinite data domain. Transducers have been extended to deal with infinite alphabets. Let's look at one such extension called streaming data string transducers. These were introduced sometime in 2010. I will not give the formal definition, but let's look at an example. So here is an example data word transformation. If the first data value and the last data value are equal, then the output is same as the input. Otherwise, the output is the reverse of the input. For example, if the input is 1831, the first data value is 1, the last data value is 1, output is same as the input. If the input is 3456, the first data value is 3, the last data value is 6, and the output is the reverse. Now let's see how to implement this data word transformation in a SDST. An SDST can have registers and variables. In this diagram, I am denoting registers by squares and variables by extended rectangles. A given SDST will have a fixed number of registers and variables. This particular transformation can be implemented using one register and two variables. Now, how does this work? The transducer will start reading its input one by one, left to right. When it reads the first data value, it is stored into the register as well as the two variables. In the register you can only store one data value, whereas in the variables you can store sequence of data values. When the second data value is read, it is appended to the first variable, it is prepended to the second variable. Similarly, the third data value is appended to the first variable and prepended to the second variable. The contents of the register are not changed. Only the first data value is stored there, and from then onwards it is not overwritten. Again, the fourth data value is appended to the first variable and prepended to the second variable. In this input, the fourth letter is the final letter, and the fourth data value 1 is equal to the first data value. The first data value is stored in the register. So the transducer can compare the current data value, the last data value 1, with the value stored in the register, which happens to be the first data value. Since those two are equal, the transducer outputs the value stored in the first variable, which is same as the input. For the other input 3, 4, 5, 6, the transducer sees that the last data value 6 is not equal to the first data value which is stored in the register, which happens to be 3. So since they are not equal, the transducer outputs the second variable, which stores the reverse of the input. So this is how SDSTs work. There are a lot of details that I have skipped, but this much is enough to understand the rest of the presentation. In this paper, we consider a fragment of SDSTs. Here I told you that the transducer can compare this last data value 6 with the value stored in the register 3. And it can say that, well, if it is equal, do something, if it is unequal, do something. It can also make decisions based on whether the current data value is greater than or less than the value stored in the register. There is a linear order on the set of data values, and the transitions of the transducer can make decisions based on the linear order, apart from just checking whether they are equal or unequal. In this paper, we drop the linear order and we only have equality and disequality between data values stored in the register and the data values that are coming in. The resulting model is what we call streaming string register transducers. Now the last term used in the title, what you need to remember. If the input is 1831 or 3456, the transducer needs to remember in its register the first data value so that it can be compared to the last one. In general, the question is, suppose you have some transduction and you are trying to implement it with a streaming string register transducer. And suppose the input is D1, D2, D3 and so on. The question is, does a transducer need to remember D1? Given the transduction F that you are trying to implement and given this input, when is it that a data value needs to be remembered? In this example, it is clear that the first data value needs to be remembered. Okay, intuitively it is clear because the first data value needs to be equal to the last data value for the output to be same as the input, otherwise the output will be the reverse. But we want a precise mathematical definition of when a data value needs to be remembered. That's what we do in this paper. It turns out that this question has been answered for automata on Datawords. So in fact there are two previous works where it is done, one by Frances and Kaminsky and another by Benedict Lay and Papis. So in fact in this paper I have borrowed a lot from this paper, including, as you see, most of the title. That paper was about processing data words, recognizing languages of data words. Here it is about transformation of data words. So let's see how they precisely define when is it that a data value needs to be remembered. Let's look at an example. Suppose you consider the language of data words, which consists of all those data words where the first and last data values are equal. So 1831 belongs to the language, 3456 does not belong to the language. Now suppose you are trying to design an automaton to recognize this language and the input is 1831. The question is, does the automaton need to remember the data value 1? To answer such a question, they said, well, replace 1 by something else and see if it makes a difference to the rest of the data word. So the input is 1831. Replace the first data value by something else. So 1831 becomes 5831. 1831 is in the language, but 5831 is not in the language. So replacing 1 by something else makes a difference. So you should remember that 1 is what you have seen. Now let's get back to transducers. To compute the output of our transduction on this input 1831, does the transducer need to remember the first data value 1? Well, replace 1 by something else and see if it makes a difference to the rest of the data word. For 1831 the output is 1831. For 5831 the output is the reverse, 1385. So replacing 1 by something else makes a difference. So 1 needs to be remembered. Good. This is not quite good enough. Let's come back to the question of automata. And let's apply the same criteria to the second data value. Replace 8 by 7 and see if it makes a difference. 1831 is in the language. 1731 is also in the language. So replacing 8 by 7 is not making a difference. So in fact you can replace 8 by anything else. It's not going to matter. So you don't need to bother remembering that it was an 8. It could have been anything else. Still the output would have been the same. That the string is in the language. So 8 does not need to be remembered. Now let's come back to transducers again. Replace 8 by something else. Replace 8 by 7. The output becomes 1731. So replacing 8 by 7 seems to make a difference. So do you need to remember 8 as well? Well, if you think about it, you should not need to remember 8. The transformation says, look at the first and last data value. If they are equal, do something, otherwise do something else. So the second data value does not play any role. You should not be forced to remember that. So this definition doesn't quite work as we expect. So it needs to be repaired. The key observation is that we should see if the replacement affects the rest of the data word, not the whole data word. Here the whole data word, the whole output 1831 is different from the whole output 1731. But what we need to observe is the part of the output that is coming from the rest of the input. We have the transducer would have read 18. What we want to see if a replacement affects the rest of the data word. The rest of the data word is just 31. So we want to check whether the way 31 is transformed, is it affected by the replacement. For that, what we need to know is which part of the output is coming from 31 and which of the output is coming from 18. In general, we should keep track of which part of the output is coming from which part of the input. That is exactly what is done in this paper, Transducers with Origin Information. So in that paper, this concept of factored outputs is used. In summary, factored outputs let us ignore parts of the input coming from some specified part of the input. Here, for example, suppose you want to ignore this part of the input 18. The output is 1831, but we don't care about the part of the output which is coming from the ignored part 18. So we replace that by star. And in 1731, if we ignore the prefix 17, the factored output will be star 31. The actual output will be 1731, but 17 will be replaced by star. Now here you see that replacing 8 by 7 is not making a difference to how the rest of the data word is transformed. The factored output is the same. So you don't need to remember whether it is 8 or 7. It could have been anything. So you don't need to remember the second data value. Let's do a sanity check and see whether this definition still works for the first data value. Do you need to remember 1, the first data value? The input is 1831. Suppose you ignore the first data value. The factored output is star 831. Now replace 1 by 5. The output is 1385. The factored output is 138 star. So replacing 1 by 5 is still making a difference to how the rest of the data word is transformed. Even though you are ignoring this part, replacement there is still affecting the output. So 1 does need to be remembered. Okay, so this is how we identify data values that need to be remembered when transforming data words. Now there are many more details that I skip due to lack of time during this presentation. But what we do is define an equivalence relation on data words. We say that two data words are equivalent if they have the same number of data values that need to be remembered for the transformation. And the data values that need to be remembered occur in the same order. Now what does it mean to say that they occur in the same order? So that is again one more detail that I'm going to skip. All the details are available in the paper. But finally the main result of the paper is a statement of this form. A transduction can be implemented by a streaming string register transducer if and only if the equivalence relation is a finite index and a few more conditions which are not as complicated as the equivalence relation. I will skip those details because this is the main point, the finite index of the equivalence relation. So this statement is similar in spirit to the classical Myhill-Nerod theorem for regular languages over finite alphabets. A similar result is known for streaming string transducers over finite alphabets, but the technique used there cannot be directly used here, although we have used some ideas. For example, the idea of factored outputs is coming from there, but not all techniques that are used there can be used here. One such example technique that cannot be used here is this two-way transducers. Over finite alphabets, it is known that streaming string transducers are equivalent to a certain class of two-way transducers, and that is used in proving a similar machine independent characterization for transformation over finite alphabets. But for streaming string transducers over infinite alphabets, there is no such two-way transducer models known. So we need to invent some other technique to deal with that. And again, I am skipping lots of more details. But from this point, a natural question that arises is, what about other models? Are there other models of transducers over infinite alphabets which do have equivalent models of two-way transducers? So one example that has been studied recently is the single-use registers. So these are devices where you can store a data value in a register, but once you use it to compare it with some other data value, you cannot use it anymore. You can use it only once. So you can read it only once. So it is known that such transducers have two-way equivalent models. It would be interesting to see how machine independent characterization for such models work. Another thing that has not been addressed in this paper is canonical transducers. In the classical Myhill-Nerod theorem, you can come up with a canonical deterministic finite automaton for a given regular language. But from the current machine independent characterization we have for SSRTs, right now we don't know if we can come up with a canonical transducer. So this is something that still needs to be explored. And another thing that needs to be explored is the technique of nominal automata. So nominal automata is another way of looking at dealing with infinite alphabets. And again, automata models and transducer models have been studied using nominal automata. So it would be interesting to see the counterparts of streaming string register transducers in terms of nominal automata. Thank you.